Welcome, everyone. Today, we are transitioning from running isolated experiments to mastering enterprise-grade orchestration by implementing training pipelines in Azure Machine Learning. Let's get started. Welcome, everyone. Today, we are focusing on a critical skill for any machine learning engineer, implementing training pipelines. So, what exactly is a training pipeline? In Azure Machine Learning, a pipeline is essentially a workflow of distinct machine learning tasks. The basics are simple but powerful. Rather than having one massive, messy script, each task in your workflow is defined as an independent block called a component. Why do we do this? In an enterprise data science process, you absolutely must separate the overall process into individual, manageable tasks to scale effectively. How is this achieved? We define the pipeline configuration using a declarative YAML file, or we can use Python functions to build it dynamically. As a deep dive, understand that these components aren't just a straight line. They can be arranged sequentially or in parallel. This enables you to build highly sophisticated flow logic to orchestrate complex, multi-step machine learning operations effortlessly. Let's take a look at this flowchart to visualize how a pipeline orchestrates tasks. At the top, we start with our raw dataset. This data flows into our first major block, the data prep component. Now, notice how the workflow branches out. Because components can run in parallel, the pipeline simultaneously sends the pre-processed data to the train model component and a separate data validation component. Both of these parallel tasks must complete before their outputs converge into the final step, the evaluate model component. This diagram perfectly illustrates the power of pipelines. By breaking the workflow into nodes, the orchestrator automatically figures out the most efficient execution graph, saving you time and ensuring that every step is executed in the exact correct order. To build a robust pipeline, you first need to understand its building blocks, components. What is a component? It is a packaged, reusable script that performs a very specific action. The basics of a component dictate that it consists of three parts: metadata like its name and version, the interface defining inputs and outputs, and the command, code, and environment specifying how to run it. Why do we go through the trouble of creating these? You do this when you are preparing your code for scale. Once experimentation is done, monolithic code must be modularized. How do you build one? You pair your Python script with a YAML file that defines its parameters. For a deep dive, think of components as an internal marketplace. Because they are modular, they allow you to easily share ready-to-go code across different users within the same Azure Machine Learning workspace, preventing duplicated effort. This block diagram breaks down the strict anatomy of a component. Look at the component definition boundary. At the top left, we have the metadata, which gives the component its identity and version history. Moving to the right, we have the interface. This is the strict contract defining exactly what data goes in and what artifacts come out. Connected to that is the command and environment block. This tells the Azure platform exactly which Docker container to spin up and what terminal command to run. Finally, an arrow points outside the definition to the actual Python training script. By isolating the script from the environment definition, the component ensures that your code runs identically every single time, regardless of who executes it. Now that we have our components, how do we stitch them together? We construct the pipeline using the Python SDK. What does this involve? It means programmatically linking our modular tasks into a cohesive graph. The basics involve using a special Python decorator called a pipeline. When you apply this decorator to a function, Azure Machine Learning automatically translates your Python code into the required pipeline YAML file. Why is this beneficial? Because data scientists can orchestrate complex routing entirely in Python. How do you start? You define a function that expects a pipeline job input. This represents your initial dataset. Let's deep dive into the data routing. The magic happens when you map outputs to inputs. You literally take the value of the output data from your first data prep step and assign it as the expected training data input for your second model training step. The SDK handles the rest. Trace the path of the data in this flowchart to understand pipeline data routing. We start at the top with our pipeline job input, which is passed into the prep data component. Notice the specific text on the arrow leaving the prep component, prep-data.outputs.output data. This illustrates how we programmatically capture the output of the first step. That exact output becomes the direct input for the train model component below it. Finally, the training component yields trainModel.outputs.ModelOutput, giving us our final trained model. This explicit chaining guarantees that the training algorithm will always wait for the data preparation to finish before it starts executing. A massive advantage of component-based pipelines is the ability to optimize compute targets. What does this mean? It means you can assign completely different cloud hardware to different tasks within the same pipeline. The basics are that you define a specific compute target, a cluster of virtual machines for your code to execute on. Why is this critical? Because data preparation usually requires massive amounts of CPU memory to parse tables, whereas model training requires expensive GPU clusters to calculate weights. Using GPUs for data prep is a waste of money. How do we solve this? In your pipeline code, you simply attach a different compute target to each component. Going deeper, because each component can be run on a specific compute target, it becomes possible to seamlessly combine entirely different types of processing power. The pipeline orchestrator handles moving the data between the CPU cluster and the GPU cluster automatically. Look at the compute architecture displayed in this diagram. The main Azure ML pipeline manages two components. The data prep component is explicitly mapped to a cost-effective CPU compute cluster. Conversely, the model training component is routed to a high-performance GPU compute cluster. Now, look at the arrows pointing to the central data store at the bottom. Even though these components are running on physically different hardware machines, the pipeline orchestrator securely mounts the same central data store to both clusters. This ensures that the CPU cluster can write the clean data and the GPU cluster can immediately read it, optimizing both your execution speed and your cloud budget. Once our pipeline is built and compute targets are assigned, it is time for execution. What happens next? The pipeline is executed as a process by running it as a pipeline job in the cloud. The basics of this execution model are hierarchical. The overarching run is called the parent job, and every individual component inside it executes as a distinct child job. Why does Azure organize it this way? Primarily for debugging and monitoring. If a massive workflow fails, you don't want to sift through one gigantic log file. How do you initiate this? You submit the job using the Python SDK or CLI. For a deep dive into debugging, if your pipeline crashes, you don't look at the parent job. If there is an issue with the configuration, you will find all the critical error information strictly within the outputs and logs of the specific child job that failed. This isolates the failure and saves hours of troubleshooting. This flowchart visualizes the execution hierarchy of a pipeline job. We start by submitting the pipeline job, which is handed off to the Azure ML orchestrator. The orchestrator spawns child job 1 for data prep. Once successful, it spawns child job 2 for model training. Notice that child job 2 is highlighted in red, indicating a failure. Both child jobs stream their telemetry independently into the workspace run history. Because of this isolation, you can immediately click into the failing child job 2 to read its specific error logs, completely ignoring the successful logs from child job 1. It is a highly efficient debugging architecture. Running a pipeline manually is great for development, but production requires automation. What do? We schedule our pipelines. The basics are straightforward. To automate the retraining of a model, you simply schedule a pipeline to run on its own. Why is this necessary? In the real world, data changes constantly. A model trained last month might be inaccurate today due to data drift. Scheduling ensures your model learns from the freshest data automatically. How is this done? You can configure schedules directly through the Azure ML Workspace UI or via code. Deep diving into the programmatic approach, the SDK provides specific trigger classes. For example, you can use the recurrence trigger class to create a schedule that strictly executes your pipeline job once per week. This guarantees continuous delivery of updated model artifacts without any human intervention. Let's follow the automated lifecycle in this diagram. On the far left, the recurrence trigger acts as our automated clock, set to fire weekly. When the timer hits, it automatically executes the pipeline job. The pipeline systematically fetches the newest dataset, then proceeds to train and evaluate the model. Upon passing evaluation metrics, it registers the updated model in the workspace. Finally, this fresh model triggers an endpoint update. This entire flow happens silently in the background every week, establishing a perfect, continuous training loop. Let's apply these concepts to a real-world scenario. Imagine you are working at Prosware, a young startup aiming to improve healthcare. You have developed a diabetes classification model that integrates with a web application to help practitioners diagnose patients quickly. But there is a challenge: patient demographics change. Whenever there is data drift or a decrease in model performance, the data science team must revise the model and update the code. Manually doing this is too slow. How do we solve it? By implementing a robust training pipeline. Prosware engineers create a data prep component to safely sanitize incoming patient records and a training component to rebuild the classification engine. By orchestrating this as a scheduled pipeline, Prosware guarantees that practitioners are always using the most accurate, medically relevant diagnostic tool available, driven entirely by automated operations. This flowchart maps out Prosware's automated pipeline logic. New patient data logs feed directly into the Prosware training pipeline. The first component sanitizes the sensitive data. The second component trains the new diabetes classifier. But notice the crucial decision gate, accuracy greater than baseline. This is an automated evaluation step. If the new model performs worse than the current live model, the pipeline branches to no, halting the process and alerting the team. If it performs better, it branches to yes, automatically registering the new model for deployment. This ensures quality control at scale. To achieve true machine learning operations, we must integrate our Azure pipelines with external automation platforms. What does this mean? It means triggering our Azure Machine Learning jobs automatically using GitHub Actions. The basics involve defining a GitHub workflow, which consists of jobs and steps that utilize the Azure CLI to communicate with your workspace. Why do we do this? Because it perfectly bridges the inner loop of data science development with the outer loop of IT deployment. How does it work? When a data scientist pushes new training code and merges a pull request, GitHub Actions securely authenticates to Azure and triggers the pipeline job. Deep diving into this architecture, automating the training portion of the inner loop ultimately allows us to quickly train and register multiple models for immediate deployment to staging environments. This is the pinnacle of automated MLOps. In our final diagram, we see the complete MLOps automation lifecycle. It begins entirely outside of Azure when a developer merges a pull request in GitHub. This event triggers the GitHub Actions workflow. The workflow securely authenticates and uses the Azure CLI v2 to send the AZML job create command. This command fires off our Azure ML pipeline job in the cloud. The pipeline executes the model training components and, upon success, triggers the automated deployment to the staging environment. By connecting Git version control to Azure pipelines, you achieve a fully auditable, highly secure, and rapidly scalable AI factory.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by Quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material. So this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see this is all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.